So this is our first lecture of Unit 1. Unit 1 is on dynamics, and dynamics is the study of motion when we consider the causes of motion. This lesson is on analyzing motion, and it covers textbook sections 1.1, 1.2, 1.3, and 1.4. And you have access to those lessons, those sections of the textbook from the course website. So we often kind of take motion for granted, but we have an innate understanding of motion. For example, you have enough experience observing basketball, for example, to know that if you throw a basketball, it follows a parabolic arc. You also react instinctively to motion. If a car is kind of moving towards you, you'll instinctively avoid the car and react. When we're talking about motion in physics, we mainly talk about the two primary fields of motion, which are kinematics and dynamics. So kinematics is the study of motion without considering the forces that produce the motion. And dynamics is the opposite. It's the study of the causes of motion. So an understanding of kinematics and dynamics is essential to understanding motion altogether. Now in grade 11, you would have studied kinematics. We didn't talk about the forces causing the motion. This course, we study dynamics. So you need to understand kinematics before you delve into dynamics, and that's why a lot of this will be review for you. But as we kind of move on, you'll start to see that there's a bit more to motion than just the kinematics you learned in grade 11. Now you may want to pause here and copy this slide down, and when you see slides with text that has this kind of 4-dot bullet pattern, that often signifies that this is important information that is worth recording down in your notes. I'll remind you when text like this shows up in the video and in future videos in this course. But for now, just a reminder, copy down the definition of kinematics and dynamics. So the two types of motion that we analyze are uniform motion, which is motion with constant velocity, and uniformly accelerated motion, which is motion under constant acceleration. That's often referred to as non-uniform motion. So uniform motion is when our acceleration equals 0. That is movement at a constant speed in a constant direction. And non-uniform motion, when acceleration is not equal to 0, it's called uniformly accelerated motion as well. And the movement involves changes in speed or direction or both. Now again, you see that that special 4-dot bullet pattern. That implies that these definitions are worth copying down. So you may want to pause in order to copy those down. Another way to analyze motion is through graphs. And you would have done this last year in grade 11 as well. But these three graphs that you see here, the one on the left is a position time graph. The one in the middle is a velocity time graph, and the one at the right is an acceleration time graph. Now when we have a position time graph, if we find the slope of the line at any given point, that gives us the velocity being traveled at that specific time. And on a velocity time graph, if we find the slope at any given time, we then find the acceleration at that given time as well. So we can turn a position time graph into a velocity time graph by finding the slope of the line at all points, or slope of the curve at all points. We can turn a velocity time graph into a acceleration time graph by finding the slope of the velocity time graph at all points as well. Now this works going backwards the same way. To find the velocity time graph from an acceleration time graph, we can find the area under the cumulative area under the graph at that point. And the same thing can happen with a velocity time graph. If we want to turn that into a position time graph, we can find the area underneath the velocity time graph at each point, and that can give us the position time graph. Now here's another slide you may want to copy down. This simplifies it into a nice graphic. So the dt graph, finding the slope of that gives us a vt graph, and finding the slope of a vt graph gives us an at graph. Finding the area underneath the curve of an at graph gives us the VT graph, and find the area underneath the curve of a VT graph gives us a DT graph. Now remember, the area is cumulative, so that means that it's not the area, not necessarily the area at a specific point, but the area cumulatively added up to that point gives us the velocity or position at that time. So another way to study motion of an object is to use those kinematic equations that you would have studied in grade 11. Now there's a slide here that has them all listed. This may be worth copying down as well, so you may want to pause and do that, but I'll also talk about our formula sheet for the course at this point. If you haven't printed out the formula sheet, which you can use during all tests and assignments during this course as well as the final exam, I recommend you do print that out. It includes these kinematics equations and equations for that will be used throughout the course as well. So we can analyze motion in 1 dimension, 2 dimensions, or more. Let's look at 1 dimension first. So that could be up, down, forwards, backwards, left, or right. When we're looking at motion in 1 dimension, you can use a plus sign to indicate the positive direction and negative sign to indicate the negative direction. And it's also important to list the direction of your measurements as well. So here we see a picture. It looks like it's a series of displacement vectors. So we have a displacement vector going from the home to the store. That looks like it's 200 meters north. That's the displacement vector labeled delta D1. We also have a displacement vector, delta D2, that looks like it's the displacement between the store and the friend's house. That's 600 meters south. Now, 200 meters north, for example, if we wanted to write that as a negative number, that's equivalent to negative 200 meters south. When we're writing down our vectors, and we're talking about 1 dimension, the negative sign also indicates a 180-degree change in the direction. So keep that in mind. Now, a 2-dimensional problem might look something like this. Here we have 3 displacement vectors, a delta D1, which is 8.5 meters east, added to a delta D2, which is 12 meters south, added to a delta D3, which is 13.5 meters west. Now, any 2-dimensional problem can be turned into a series of 1-dimensional problems. So here, it's showing us the resultant displacement. We can calculate that later. We'll look into how do we do that. But what you can see here is that we have a one displacement that's completely in the vertical direction, north-south. That's 12 meters south. And then 2 that would be compared here, 8.5 east and 13.5 west. Now, if we add those 2 together, we have to keep in mind that let's take east as our positive, for example. 8.5 east plus 13.5 west would be the same as 8.5 east minus 13.5 east. Adding those together, making sure that we keep the directions consistent, will give us the total displacement in the horizontal direction, rather. So the key to solving kinematics problems is just don't be lazy. Make sure you write down what you know from the start of a problem. I also like to write down what it is I'm trying to solve for. Include directions in your solutions. So don't be lazy and not include directions. Draw a picture. Use your formula sheet. Check your answers and read ahead in the problem. Don't start solving the problem until you've fully read it and understood it.